In this lecture video, we'll learn about metal-mediated reactions and how organometallic reagents can be used to form carbon-carbon bonds. Even though we've seen a variety of ways to form carbon-halogen and carbon-oxygen bonds to make alkyl halides and alcohols, one class of reaction that we haven't really seen much is the formation of carbon-carbon bonds. And that's because carbon isn't typically a very good nucleophile, and so it won't participate in substitution reactions, for example. We saw that we can deprotonate a terminal alkyne to make an acetylide anion, and that's a good nucleophile. But this only works because that CH bond is very acidic. Most CH bonds can't be deprotonated in that way. And so to make a carbon a good nucleophile, we often use organometallic reagents. An organometallic reagent is one in which a carbon fragment is bound to a metal. And we use organometallic reagents in coupling reactions to form carbon-carbon bonds between the organometallic reagent and an organohalide. One very common kind of organometallic reagent is a Grignard reagent. And this involves a carbon-magnesium bond. A Grignard reagent can be formed from the reaction of an alkyl halide with magnesium metal. And in this species, the carbon-magnesium bond is polarized toward the carbon, so much so that we often think of this as an anionic carbon and a cationic magnesium. That means that Grignard reagents are good nucleophiles at the anionic carbon, and so will react with electrophiles. Let's take a look at this type of reaction. Here we have the reaction of a phenyl Grignard with this organic compound. And again, Grignard reagents will act as nucleophiles to form new carbon-carbon bonds. So the nucleophile here is the aryl ring, or more specifically, the electrons in the carbon-magnesium bond. And the electrophile is the carbon of the carbon-bromine bond. And just like in other substitution reactions we've seen, we can envision the nucleophile attacking the electrophilic carbon to displace the bromide leaving group and form a new carbon-carbon bond. Grignard reagents are strong nucleophiles, so in general, we expect them to proceed through SN2 type substitution pathways. Alkyl lithium reagents are organometallic reagents that are similar to Grignard reagents and will also act as good nucleophiles. We can make an alkyl lithium reagent from the reaction of an alkyl halide with two equivalents of lithium metal. Let's try an example. Predict the products that would result from the Grignard reaction shown. Here we have two steps. In the first step, the alkyl bromide reacts with magnesium metal in ether. The carbon-bromine bond will break, and both groups will add to the magnesium. And this forms the Grignard reagent. Then in the second step, the Grignard reagent will act as a nucleophile to attack the electrophile. Here we have only water, so in water, remember that the proton is the electrophilic piece. And so the Grignard reagent will attack the proton to form the alkane and magnesium hydroxide. And this reaction shown here, the reaction of a Grignard reagent with water, means that if you're trying to use a Grignard reagent to do a coupling reaction, like we saw on the last slide, it's really important to make sure you have no water around in your reaction mixture or in your solvent, because the water will quench the Grignard to give you the alkane instead of the coupling product. The second kind of organometallic reagent we'll look at are organocuprates, or compounds with carbon-copper bonds. And one of the most prominent examples here are Gilman reagents. These are diorganocopper salts of lithium, and they will also couple with organohalides to form new carbon-carbon bonds. But here, these reagents can couple with alkyl, vinyl, or aryl halides. Grignard reagents can only couple with alkyl halides. And so Gilman reagents are much more versatile because they can couple with a wider variety of organohalides. And an example is shown here at the bottom. This dimethyl cuprate will react with phenyl iodide to couple the methyl and phenyl groups. or to form a new carbon-carbon bond between the methyl and the phenyl. Finally, the last class of organometallic coupling reaction that we'll see are Suzuki reactions. And these are palladium catalyzed reactions. These reactions couple an aryl halide with an aryl boronic acid. This is a catalytic reaction, meaning that the palladium catalyst is not consumed or changed during the course of the reaction. And when we draw a mechanism for a catalytic reaction, what we draw is a circle, a catalytic cycle. We draw a catalytic mechanism from the perspective of the catalyst, here from the perspective of the palladium. For a cross-coupling reaction, the first step is reaction of the palladium catalyst with the aryl halide to generate a palladium aryl intermediate. In the second step, this palladium aryl intermediate reacts with the aryl boronic acid to form a second palladium aryl or palladium carbon bond. Then in the final reaction step, the product eliminates from the palladium center to form the new carbon-carbon bond, and the palladium catalyst returns to the cycle to activate another alkyl halide. So in a catalytic mechanism or a catalytic cycle, the starting materials are indicated as entering the cycle, and the products are indicated as leaving the cycle. We'll end this video with the question we saw at the beginning: to predict the products of the following reaction. This reaction features an organocuprate. And remember that these react with carbon-halogen bonds to form new carbon-carbon bonds. So in your reactant here, the acyl chloride will cleave the carbon-chlorine bond and will form a new bond between the benzyl carbon and the acyl carbon.